Okay, so I couldn't see my little arrows to move it. All right, so today we're going to talk about acceleration. We're going to talk about position versus time graphs, and we're going to talk about velocity versus time graphs. So, for acceleration, all right, acceleration is the rate. Let's see if I can get a pointer. I don't know if you can see my pointer or not, but acceleration is the rate at which the velocity changes. So in this particular case, we don't have velocity, we have speed. Speed, you guys type in the chat box there. What is speed in comparison to velocity? How fast you're going? Okay, what else? What else do you know about speed? Miles per hour, miles per second, feet per second, inches, you're right. It's that type of rate because it's always with respect to time. So it's the distance traveled over time. The other thing that you know, and this is kind of important to remember, is that speed is a scalar, right? You can only, it's only positive. It's never negative, so it doesn't have any direction, okay? And velocity, if speed is scalar, what is velocity? Yes, velocity is the vector. It's the same sort of definition. It's still the distance traveled over time, but velocity has a direction. So anyway, let's go back here. If we start at time 1 second, your speed is 1 kilometer per hour, then it's 1/1. So if you look at this, 1/1, remember acceleration is velocity divided by time, we get 1 kilometer per hour. However, if we looked at it this way, if we started at 0, after 1 second we're going 2 kilometers per hour, after 2 seconds we're going 4, then our acceleration is 2 kilometers per second. All right. So acceleration and velocity are completely different ways to describe the way something is moving. Now, an object can be accelerated even when its velocity is 0. And by that, I mean, if you think about this, when you throw a ball, so I'm going to put it up here. I don't know if this will even work. Okay, so I'm going to throw a ball. This isn't working. Anyway, so if you throw a ball and you throw it up in the air, right? As it goes up in the air, it's accelerating, but it's slowing down. Think about it, because the higher up it goes, the slower it goes. When it gets to the top, it's changing direction. Now it's going up, now it's coming down. So even when it's at the top, okay, even when it's at the top, it still has that gravity, that acceleration due to gravity. So it's still, an object is still accelerating even when the velocity is 0. I think that's kind of cool. Can the velocity be 0 when it's not changing position? The only way that that's happening is if you're just standing still, if you're not moving. Does that make sense? But the second bullet here is talking about when something is moving. So when it changes direction for that instant that it's changing direction, then the velocity is changing. The acceleration, the velocity is, let me read. At the instant that an object is changing its direction, okay, then that's the velocity is 0, but there's still the acceleration there. There's still that little bit of acceleration. And if you're thinking about a ball being thrown up and then coming back down, at the very top, it's changing position. And the acceleration, there's still that acceleration due to gravity, pulling it down. If you think about the fact that, you don't fall over or you don't fall through the earth because you are still accelerating, that gravity is pulling you down. Okay, so like velocity, acceleration can be positive or negative, so that tells us that acceleration is a scalar. I'm sorry, is a vector. If I make a mistake, you guys let me know. So an object will have positive acceleration when it's speeding up in a positive direction, and negative acceleration when it's slowing down in a negative direction. Okay, so this is the formula for velocity. I'm sorry, for acceleration. I'm looking at velocity. Acceleration is velocity final minus the initial, all divided by the time that it takes for it to change the velocity. All right? And this is important. The units for acceleration are meters per second squared. And we're going to go over a slide that tells us how we get this. All right? So this right here is an important calculation or important formula to have on a formula sheet. All right, so let's look at some calculating acceleration. So a sailboat moves at 1 meter per second, and then the wind comes up and its velocity is changing to 4 meters in 3 seconds. We're going to calculate the acceleration. So what I want you guys to think about is what goes where. All right? So I don't know if I can draw on here. I can't seem to draw. We'll see. All right, so velocity final is going to be 4 meters per second. All right, velocity initial is 1 meter per second. And our time is 3 seconds. Okay? Everyone good with that? No? Jamie, you're not good with this? All right, tell me why. Give me... All right, so what we're looking at here, we're just reading the problem. And it says that a sailboat moves at 1 meter per second. So right up here at this picture, do you see this picture up here at the top? When time is 0, this little boat is just moving along. There's just a slight breeze, and the boat is moving at 1 meter per second. Okay, so that's its velocity. All right, then there's a wind that comes up, right? The wind is coming up, and so when you think about a sailboat, then you have to remember that when the wind comes up, everything starts moving faster. So the wind is coming up, and after 3 seconds, all right, 3 seconds, now that boat is moving at 4 meters per second. All right, so what we want to know is what's the acceleration? How fast did it move, or what was the acceleration between 0 and 3 seconds? So my initial velocity was 1, my final velocity was 4, and the time was 3 seconds that it took to do that. Okay? All right, so let's look. So we're looking for acceleration, and acceleration is meters per second divided by seconds. Because let's think about that. This is our velocity, and this is our time. Okay, so we're given that the initial velocity was 1, the final velocity is 4, and the time is 3. Alrighty, So remember that this was our formula that we had. We saw that on the last slide. And so all we have to do is some calculations. So meters per second, all right, thank you. Meters per second divided by 3 seconds, right? There we go. Okay, does that make sense? Smiley face, yay, thumbs up, something. Excellent. Excellent, okay. So, again, this is the formula right here. Acceleration is velocity, the final velocity minus the initial divided by time. And what we're looking at is the change in speed over the change in time. And then how do we get these units? Units are pretty important in physics because they really tell you, they help you with your calculations. All right? So we're going to plug in some values. So we're going to say that our acceleration is, the velocity is 50 meters per second in 1 second. So this is how we get our final units. 50 meters per second. And you guys remember from, oh, I don't know, maybe it was way back when, 8th grade, maybe last year, I don't know. I don't remember when you would have learned. When you have a fraction divided by something, it's something over 1. So to do that division, we actually flip the denominator and multiply. Maybe you learned the formula copy, dot, flop, and you flip this denominator. So what we get is meters per second times second, which is meters per second squared. All right? So that's how you get meters per second squared. And that's acceleration. So the acceleration in meters per second is this way. It's a lot nicer. I always write it like this. But if you really want to, you can write it like this. It doesn't matter. Hi, Katie. How are you? All right. And we already went over how we got it. So now what we're going to look at is some position, velocity, and time graphs. So this particular graph, what we're looking at is height and time. Or we could call this, if not height, it could be position, right? Position meaning that, I'm trying to write sideways. Not bad. All right. So this is in meters. So this, whatever it is, stone or ball or book or something, is starting out at 1 meter. So they're dropping it from maybe a table. And it's falling to the ground. And it falls to the ground in less than half a second. All right? So that's what we're looking at in this graph. So the key question here is, how are graphs used to describe motion? So we're going to create graphs of velocity versus position. Oh, no worries. No worries. Thanks for coming. Stay. Don't leave. Okay? And then we're going to create a predictive model for velocity of a rolling car down a hill, I think. Okay, so position versus time graphs. The motion graphs are an important tool to show the relationship between position, velocity, acceleration, and time. So if we have position and time, and we have these two cars moving, this car A, if you look at it, in 5 seconds, it went further, right? It went 10 meters. And car B in 5 seconds only went 5 meters. So car A was going faster. All right, so then this one was going slower. So car A's velocity was faster. And when you look at the graph, what this is gonna tell you is, if you guys remember about slope, give me a smiley face or something. Do you remember about slope? Yes, excellent. So the steeper the slope, the faster you're going. All right. So graphs help test drivers and engineers see how much straight track each car can cover in equal amount of time. So, that's how they get it can go from 0 to 60 in 5 seconds or something. It tests it. All right. And then drivers can make adjustments on how they operate their cars. So graphs are pretty important for manufacturing. The slope of a line, all right, is the ratio of rise, or the vertical change, to run, the horizontal change. And if we look here, the rise is equal to the height of a triangle. The run is equal to the length along the base of the triangle. So for this particular case, what we have is that our slope is rise over run. So our height is 10, our length is 5, so this particular car was going 2 meters per second, and that's the speed. Position versus time graph tells you whether an object's velocity is constant or changing. In this particular case, both of our cars have constant velocity. And it's constant because the slope is the same all along this line. Not a very good straight line. And it's also straight. It's constant. The slope changes all across that line. Exactly. B has a velocity of 1 meter per second. Thanks, Katie. That was good. Okay. So if the velocity is constant, the graph is going to be a straight line, constant slope. So I don't know if you guys remember this from your algebra, 8th grade, 9th grade, but there was a reason that you were doing slope, and you never knew it. So if the velocity is changing, then the slope is changing. So the graph of the curves are also changing. And in this particular case, what we see is that we have a ball, and instead of saying, okay, we're starting at 200, what we're doing really when you look at this graph is you have a little guy up here, okay, and he's letting go of a ball. He's just dropping a ball. But what they're doing is, this is our 0 point, and down here they're calling 120 meters. Okay, so you don't get confused. They just switched the positions. They're starting at 0. Okay, so what happens here is, when you start to drop this ball, it goes slow at first, and then it speeds up until it gets down to the end. All right? So that's why this curve is curved instead of straight. This line is curved instead of straight. It's starting out slow, and then it's speeding up. Okay, can you look at the graph and see how the slope down here is not very steep, and as it goes up higher, it gets steeper, so it gets faster. Excellent, you see, there was a reason for your math. All these people that say they don't know why they're doing their math. Okay, so the graph of an object is slowing down, so is the curve. In this particular case, if you think about throwing a ball up in the air, when you throw it up in the air, it goes really, really fast. And then as it gets to the very top, when it's going to change or come back down, then it slows down. Oops. I have to watch that. Okay. Another example is a car coming to a gradual stop at a red light. If you think about it, when you are driving your car, you're going pretty fast, and then you start slowing down. All right, your velocity is changing until you stop. All right. So speed and distance traveled. So here we're looking at speed. This car, truck, person, whatever, is going at a constant speed. Whoa, I don't know what's going on here. It's going at a constant speed. All right. All right, guys. That's enough of that. All right, so your area under the curve is actually the distance that you've gone. So if you're moving at a constant speed, then the area is 10 seconds, that's the time, times 1 meter per second, that's how fast you're going. So you've traveled 10 meters. And again, if you look at this, seconds times meters per second, this is where your units are really handy. That's how you get your distance. Okay, so that really, it's kind of important. So now we're going to look at position, velocity, and more time. So what happens to the velocity of an object that moves downhill? So we're going to explain the motion of the energy car in terms of velocity and acceleration as it moves along an inclined track. So infer the meaning of acceleration from the velocity versus time graph. So acceleration, just like with position versus time, the slope of the line was the velocity. When you look at a graph of velocity versus time, the slope of that graph is the acceleration. So many uses for slope, I just can't. It's just exciting. Okay, so we're going to apply the acceleration formula and we're going to solve some problems. So the velocity versus time graph has velocity on the y-axis, and again, it is important to label your axes so you know what you are graphing, so that the person that is looking at your graph knows what you're talking about. So in this particular case, we have a velocity, right, that's constant over a specific amount of time. Okay, so if you have a horizontal line, that means you have a constant velocity. So velocity versus time is the best tool for understanding acceleration, and it clearly shows how the velocity of an object changes with time. So down here we have some positive velocity, so it's speeding up. Over here we have negative velocity, and negative velocity, the slope is negative, so we have negative acceleration, so it's slowing down. And then right here, if your velocity is constant, then you're not accelerating at all. You're still moving, you're just not accelerating. So this is a picture of this person dropping the ball like I kind of showed you before. The velocity versus time graph shows this is a ball. This little guy is dropping down this ball, and it's in free fall. The reason that it's in free fall is because he's not throwing it down, he's just letting it fall. He's just dropping it. There's no, when you think about it, there's no velocity at the beginning. When you just drop something, it just starts falling. So since the ball is accelerated by gravity, its velocity increases by the same amount each second. So after the first second, right, its velocity is 9.8. After the second, its velocity is 19.6. After the third second, its velocity is 29.4. So what about after the fourth second? What is going to be its velocity? You see what we're doing here? Each time, just in case, we're adding 9.8. Anybody? Anybody? 9.8. So what's the... Oh, I'm sorry. 39.2. Yes, Shay. Sorry, Jamie. Okay, so free fall, starting at rest, your velocity is 0, right? And what happens, this is the formula for free fall. Velocity is equal to gravity, which normally we say 9.8 meters per second squared. This is obviously SI units, but if we're using English units, it's 32.2, I think, and then it's feet per second squared. All right, so I would say in 99 out of 100 times in physics, you're always going to use SI units, meters, centimeters, millimeters, kilometers, liters, that kind of stuff. You're not going to use feet unless the problem starts out that way. So after 1 second, it's 9.8 because your t would then be 1. G is always going to be a constant, 9.8. After 2, and so on. All right. Constant acceleration. Constant acceleration, don't confuse that with the velocity. Constant velocity means that an object's position changes by the same amount each second. But constant acceleration means that an object's velocity changes. And if you think about, again, that really helps whenever you have your axes labeled. Okay, so calculating acceleration, the slope of the velocity versus time graph represents acceleration. So in this particular case, we have a constant acceleration because the slope is never changing. The line is a straight line. Again, you calculate the slope the same way, rise over run. And for us, we're only going to be able to calculate slope of straight lines. You need calculus to do those curved lines, but you can still describe the motion, even though, you can't say at this specific time it was, the acceleration was this much. So again, rise over run. Rise is the amount of velocity and run is the amount of time. So calculating the acceleration from the graph. So what we can see here, look for some place where you can actually see a point. And in this particular case, the only place that I can really say I see it crosses is when the velocity is 40 and the time is 10. So our acceleration here is 40 meters per second squared. Quick review. Displacement is equal to the area under the graph of the velocity versus time graph. That's your displacement. I don't believe we will be doing this, but you know what? It's pretty easy to calculate. If you have a velocity and a time graph, in this particular case, the area of a triangle, right? 1/2 the base times the height. So the displacement is just 2 meters. It's pretty easy to calculate, and again, it's important for being able to read the graphs and showing that it's not just torture, it's a lot of fun. Okay, so to show the direction or velocity of a time graph, we must include a portion of the graph that shows negative velocities. So what we have here, it's kind of hard to see, we have position versus time. Since we have right here a straight line, our velocity is constant. And that's why you have this horizontal line in your velocity versus time graph. As this little car moves away from the sensor, as it moves back toward the sensor, we have some negative velocity going on, and so you have negative, a negative horizontal line. These are just pictures, and just to show you position versus time. If there is no motion, if you're just standing still, this is what the graph would look like. Your velocity is going to be 0. If you have a constant velocity and you're moving forward, then you have, you have a constant straight line. If you're moving backwards, then you have a negative line. If you're speeding up, so you start slow and go real fast, or up here you're going to start slow and go real fast. What you have here is positive velocity, and here you have some negative velocity. If you are slowing down, so you're starting really fast and then slowing down, and here you're still starting really fast and slowing down, but you're going backwards. All right, so these are just pictures of graphs and to help you to understand a little bit about what's going on. All right, so this is the connection to the real world, and then we're done. The more we learn about how animals interact with the environment, the better decisions we can make about how we use the oceans. So satellite tagging research have studies have led many new laws and guidelines to governing human activities around endangered species. So what happens is that these tagging things that they use, they can graph the position, they can graph where these animals are, they can say how fast they're moving, and then they can decide, what is the best way to help these animals, where are they going, what's going on. Alrighty, guys. So, any questions? All right. You guys are doing really well, so I have to commend you. And thank you for coming, so I didn't have to talk to myself. You guys have a great day. Yes, you can do that. And I think it was just the units. Alrighty, guys.